Welcome to the deep dive. Today we're tackling thermoelectricity. That's the fascinating science of turning heat directly into electricity, and also the other way around, using electricity to pump heat, create cooling. Think of it as a solid state way to manage temperature. And the key players here are two main effects. The Seebeck effect, where a temperature difference makes a voltage, and the Peltier effect, where applying a voltage makes heating or cooling happen.
Exactly. And our guide for this deep dive is, well, it's a book by someone who's clearly spent a long time in this field, over 55 years of experience. What really jumps out is how practical it is. The author really wants to get past just the theory, look at how this stuff actually works.
Right. So our mission today basically is to get a solid handle on the fundamentals. We want to understand the key materials and, drawing on this author's perspective, figure out the challenges and, maybe more importantly, the really exciting potential here. Okay, let's dive in. Where does this whole story really start?
Well, the story kicks off way back, early 19th century, 1821, Thomas Seebeck. He made this really interesting observation. Notice that if you have a temperature difference between two different metals, it could actually make a compass needle move. What he was seeing, though he didn't quite frame it that way then, was a magnetic field from electric current produced by that temperature difference.
Just from a temperature difference.
Yeah. Then, maybe a dozen years later, a French watchmaker, Jean Peltier, saw the reverse. He found that if you run current through a junction of two different materials, it could get hotter or colder, depending on which way the current flowed.
A watchmaker. That's amazing. Shows innovation pops up anywhere. You mentioned it was tough to really demonstrate the Peltier effect clearly back then with just metals. Why was that?
Right. Well, the thing is, the Peltier effect in metals, it's pretty small. And it's always kind of mixed up with regular Joule heating, the heat you always get when current flows through resistance.
Yeah.
So trying to isolate that specific cooling or heating from the Peltier effect, it was a real challenge. Sometimes the best you could do was just show there was a bit less heating one way than the other. It wasn't really obvious.
Until
we started working with semiconductors. That's when the Peltier effect really became much more pronounced. Suddenly, you could actually build practical refrigerators based on it.
Semiconductors, the game changer. What was so special about them?
They just have these unique electronic properties, sort of halfway between metals and insulators. And this allows for much, much stronger thermoelectric effects compared to metals. That breakthrough is really what made practical Peltier coolers and thermoelectric generators, well, possible, at least for niche applications. Though it's worth remembering, they haven't historically been as efficient as, say, your standard compressor fridge or a big power plant turbine.
Okay, so when we talk about these effects, how do we actually quantify them? I think I saw something about coefficients.
Yes, exactly. For any pair of conductors, let's call them A and B, we define a few key coefficients. First, the Seebeck coefficient, usually written AB. Think of it as volts per degree Kelvin, how much voltage you get for a temperature difference. Then there's the Peltier coefficient, AB. That tells you how many watts of heating or cooling you get at the junction per amp of current.
Okay, Seebeck is voltage from heat. Peltier is heat from current.
Right. And here's the neat thing, they're related. One of the Kelvin relations shows that the Peltier coefficient is just the Seebeck coefficient times the absolute temperature. So AB equals AB times T.
That's handy, and no one, you can find the other. What about the Thomson coefficient? That was mentioned too.
The Thomson coefficient. That describes heat absorbed or released within a single material when current flows through it, and there's a temperature gradient along it. And the other Kelvin relation connects the difference in Thomson coefficients, take T, to how the Seebeck coefficient between them changes with temperature, T times dB dt.
Yeah.
These Kelvin relations are, well, they're pretty fundamental, show how all these heat and electrical things are tied together.
It sounds like we're always comparing pairs of materials, A and B. Can we talk about the properties of just one material?
That's a good point. Yeah, we can. While the coefficients are defined for a pair, we can get absolute Seebeck and Peltier coefficients for a single material. The trick is to use a superconductor as the reference point, because the thermoelectric coefficients between any two superconductors are zero. So pair your material with a superconductor, and voila, you isolate the properties of just your material.
Like using a 0 point on a scale. Clever. Okay, so moving beyond the basics, how do we judge how good a material or a pair is? The figure of merit came up.
The figure of merit. Yes, very crucial. When you build a device, say a cooler, from a P-type and an N-type material, a thermocouple, its figure of merit, Z for the pair, tells you how efficient it can be. Essentially, you want to minimize the combined thermal and electrical resistance of the two legs of the thermocouple. And when you optimize that mathematically, you get this Z value that depends on the Seebeck coefficients and thermal conductivities of both P-type and N-type materials.
Okay, so Z is for the pair, but there was also a Z is lowercase z.
Right. Lowercase z is the figure of merit for a single material. It's defined as a Z. Alpha squared times electrical conductivity sigma divided by thermal conductivity lambda. You see Z's used a lot when people compare individual materials. But, and this is really important, the author stresses this, you can't just take the Z's values for your P-type and N-type and calculate the device performance. You need the combined factor of merit, Z for the pair. It's the system that matters.
Got it. Z for the team, Z for the players, but Z wins the game. Okay, now, the outline also mentioned thermomagnetic effects. Nernst and Eddingshausen, how do they fit in?
Right, these are effects that pop up when you have a magnetic field involved as well. Take the Nernst effect. If you have a temperature gradient along a material, and you apply a magnetic field perpendicular to that, you can get a voltage appearing across the material, perpendicular to both the heat flow and the magnetic field. And interestingly, the sign of this Nernst voltage doesn't care if the charge carriers are positive or negative, unlike the Hall effect.
And Eddingshausen.
That's kind of the reverse. You run a current through the material, apply a perpendicular magnetic field, and you can create a temperature difference across the material, again, perpendicular to both current and field. Just like Seebeck and Peltier are linked, Nernst and Eddingshausen are also related through another thermodynamic relation.
The outline mentioned Eddingshausen coolers. How did those actually work?
Okay, so imagine a bar of a suitable material. You run current along its length, apply a magnetic field across its width. The Eddingshausen effect then forces heat to move sideways to one of the faces. So one face gets hot, the opposite gets cold. Attach a heatsink to the hot side, put what you want to cool on the cold side, and you've got refrigeration. There's even been talk about making multi-stage or continuously graded coolers by shaping the material carefully.
Sounds like a different way to get cold, for sure. Then the outline shifts to the fundamentals of the materials, metals versus semiconductors. What are the key differences thermoelectrically?
Well, it really comes down to their electronic band structure. In metals, you've got this conduction band that's only partly filled with electrons, so they move easily. Semiconductors have a filled valence band, an empty conduction band, and this energy gap in between. Electrons need a boost of energy to jump the gap and conduct. Insulators, huge gap, very hard for electrons to jump. Then you have holes in semiconductors, basically missing electrons in the valence band acting like positive charges. And the Fermi level, sort of the average energy level, sits in the conduction band for metals, in the gap for semiconductors.
And how does that structure affect heat transport?
Heat in solids is carried by electrons and by lattice vibrations, phonons. In metals, with lots of free electrons, they dominate both electrical and thermal conduction. In semiconductors, it's more balanced. Both electrons and holes and phonons carry significant heat. And how these carriers interact, how they scatter off lattice vibrations or impurities, is super important for thermoelectric properties. It affects conductivity, but also the Seebeck coefficient.
Right, scattering. The outline mentioned relaxation time, tau.
Yeah, relaxation time. It's basically the average time an electron or hole travels before it gets scattered, bumps into something like a vibrating atom or an impurity. It's a measure of how freely they move. And this time often depends on the carrier's energy. We often write it as E times E to the power of R, where R depends on what's doing the scattering. Like if it's acoustic lattice vibrations, R is typically magnitude 12. If it's charged impurities, R is more like 32. Knowing the main scattering mechanism is key because it really dictates the transport properties.
Okay. And then some heavier physics, Boltzmann equation, Fermi-Dirac statistics. What's the gist for us?
Okay, think of the Boltzmann equation as the master equation. It describes how the distribution of electrons changes when you apply fields or temperature gradients, taking scattering into account. It's the tool for calculating transport coefficients. And Fermi-Dirac statistics, that governs how electrons fill up the available energy states because they're fermions. No two can be in the exact same state. The key point for thermoelectricity is that it's mostly the electrons near the Fermi level that participate in transport. So together, these give us the theoretical framework to understand how electrons respond.
Boltzmann is a rule book. Fermi-Dirac tells us which players are active. Got it. Then we get into optimization, starting with the power factor, alpha squared sigma. How do we max that out?
Right, the power factor, hugely important. It tells you how much electrical power you get out, generator, or how much cooling power you get, cooler. High power factor is essential. But here's the catch. Seebeck coefficient and electrical conductivity often work against each other. Like, if you add more dopants to a semiconductor, sigma usually goes up good, but alpha might go down bad. So optimizing is about finding that sweet spot, the right doping level or carrier concentration that maximizes the OS product. Interestingly, the book notes the ideal Fermi energy for this maximum is often quite close to zero energy, near the band edge.
That feels a bit odd. Wouldn't you want lots of carriers, a high Fermi energy?
You'd think so, wouldn't you? But it's not just the number. It's also their energy distribution relative to the Fermi level. A higher Fermi energy means more electrons, sure, but their average energy difference might not be ideal for generating the biggest Seebeck voltage. So sometimes slightly fewer carriers, but with a better energy setup, gives you the best overall power factor.
Okay, interesting trade-off. The outline then brings in this materials parameter, beta. What does that represent?
Beta is a kind of fundamental indicator of a material's inherent thermoelectric potential. It bundles together things like carrier mobility, effective mass, how carriers respond in the crystal, and the lattice thermal conductivity. And this beta is directly linked to the dimensionless figure of merit, ZKT, which is our main performance metric. Basically, higher Bay means higher potential ZT. The exact link also involves that scattering parameter we mentioned.
And how does the optimum Fermi energy connect to this Beta parameter?
What's kind of cool is that over a pretty wide range of Beta values, the optimum Fermi energy doesn't actually shift around that much. It tends to stay in a fairly narrow range, maybe around KT, the thermal energy. This suggests the ideal Seebeck coefficient for high performance might be surprisingly consistent across different materials, which is a key insight. It means just finding a material with a massive Seebeck coefficient isn't the whole story. You might need to tweak its conductivity, even if it lowers alpha a bit, to hit that optimal balance for high ZT.
So BATE is the raw talent, ZT is the performance score linked via Beke.
Got it. Then carrier mobility and effective mass, why are they so critical?
Carrier mobility, moo, Bebe. That's how easily carriers move under an electric field. Higher mobility generally means higher electrical conductivity, which we want. Effective mass, Abe, that's how electrons or holes feel the crystal lattice. It's not their free space mass. It can be different depending on the material direction. We talk about density of states mass, Amen, and inertial mass, Mi. They're related, but not always identical. And how mobility depends on effective mass links back to scattering. For example, with acoustic scattering, mobility often goes like Mn to the power of -52. So a lower effective mass gives higher mobility in that case.
And lattice thermal conductivity, we want it low, obviously.
Yeah.
What controls it? Right, LL. That's the heat carried by lattice vibrations, the phonons. We absolutely want to minimize this. It depends on temperature, how strongly atoms are bonded, atomic masses, and crucially, any defects or disorder in the lattice. The outline mentions the slack relation, kind of a rule of thumb to estimate LL based on things like demi-temperature, related to vibration frequencies, average atomic mass, and atomic spacing. Gives you a rough idea.
So it's this constant balancing act, high electrical conductivity, low thermal conductivity, all interconnected, complex stuff. The outline then highlights the energy gap, egg. Why do we need to worry about that?
The energy gap, egg, is that forbidden energy zone in semiconductors. It's vital for preventing mixed conduction. That's when both electrons and holes are carrying significant current. If that happens, their Seebeck coefficients, one usually negative, one positive, tend to partly cancel each other out. Bad for the overall alpha, bad for ZT. So to avoid this at your operating temperature, the gap needs to be big enough, rule of thumb. At least 6 times KT, the thermal energy, keeps one carrier type dominant.
Makes sense. And non-parabolic bands. We usually see nice, simple parabolas for energy bands. Reality check.
Yeah, the simple parabolic band picture is an approximation, good near the band edges. But in reality, especially if the gap is small, or for carriers with higher energy, common in doped thermoelectrics, the relationship between energy and momentum gets more complicated. Non-parabolic. This makes the theory much harder. While we hope it's mostly the near-edge carriers doing the work, non-parabolicity might explain sometimes when simple theory doesn't quite match experiments.
Okay. The outline then loops back to thermomagnetics, Eddingshausen, and Nernst coefficients expressed using Hall mobilities. How does that help?
The Hall mobility, Ca, characterizes carrier movement when you have both E and B fields. It's related to drift mobility but can differ, especially with mixed conduction. It turns out you can mathematically express the Eddingshausen and Nernst coefficients using these Hall mobilities, carrier concentrations, and things called Hall factors. These links help us understand and maybe predict how magnetic fields can manipulate heat and charge flow, crucial for designing thermomagnetic devices.
And finally here, superconductors as passive thermoelements. That sounds intriguing.
It is. The idea is to leverage their zero electrical resistance below their critical temperature. Great for cutting Joule heating losses. But to be useful as passive parts like connectors, they also need low thermal conductivity. Don't want them shorting the temperature difference. And high critical current density. Need to carry current without losing superconductivity. The example I mentioned is pairing a high TC superconductor like bismuth with a conventional thermoelectric like bismuth. The superconductor acts as a super efficient electrical path, potentially boosting overall system performance, maybe especially if a magnetic field is also involved.
Fascinating. Okay, let's switch gears to strategies for minimizing that unwanted thermal conductivity. First up, solid solutions. What are they? How do they trap heat?
A solid solution is basically an alloy, mixing two or more semiconductors with similar crystal structures. Think bites mixed with sectes. The idea, championed by IOF way back, is that this atomic mixing creates disorder in the lattice. This disorder acts like speed bumps, scattering the short wavelength phonons that carry most of the heat. But, and this is key, the longer wavelength electrons carrying the electricity might pass through relatively easily. So you knock down the lattice thermal conductivity without hurting the electrical conductivity too much, hopefully. Examples like bites at speeds for p-type and biphase for n-type are classic examples, still widely used.
So a bumpy road for heat, smoother highway for electricity. Nice analogy. What about scattering from point defects? What kind of tiny flaws are we talking about?
Point defects are just single atom scale imperfections. A missing atom, vacancy, an extra atom squeezed in, interstitial, or a wrong type of atom swapped in, substitutional impurity. These disrupt the perfect lattice rhythm, changing how it vibrates and scattering phonons. How well they scatter depends on the size difference, the mass difference compared to the host atoms, causes strain and mass fluctuations. For phonons much bigger than the defect, it's like Rayleigh scattering how the sky is blue, scattering light off tiny air molecules.
Okay. And boundary scattering. Where do these boundaries come from?
Boundary scattering kicks in when the distance a phonon travels before scattering its mean free path becomes comparable to the physical size of the grains in a polycrystalline material. Think the interfaces between these tiny crystals, or the surface of a thin film. When phonons hit these boundaries, they scatter. This is especially effective for low-frequency, long-wavelength phonons that aren't scattered much by point defects. So making materials with very fine grains increases the boundary density, boosts scattering, and lowers thermal conductivity. We saw this helps in Seebeck alloys, for instance.
Right. The outline notes that things scattering electrons often scatter phonons too. Is that a general problem?
Yeah, it often is. Many things that hinder electrons' impurities, lattice vibrations, also hinder phonons. They interact with the same lattice imperfections. So you might add something to boost electrical conductivity, but oops, it might also reduce phonon scattering, increasing thermal conductivity. Exactly what you don't want. It's a fundamental trade-off you constantly battle in material design.
What about using fine grains and large unit cells in the crystal structure? How does that combo work?
Materials with large, complex unit cells, the basic repeating block of the crystal, tend to have more complicated vibration patterns. More optical modes, in addition to the main heat-carrying acoustic modes. These optical modes are usually slower, don't carry heat as well. Now, if you make such a material fine-grained, the grain boundaries scatter the main heat carriers, acoustic phonons, because the inherent vibration physics is already complex in large unit cells. Comparing fine-grained versus large-grained versions of the same material often gives more insight than simple scattering models.
Which leads nicely to the phonon glass electron crystal, or PGEC concept. Sounds like the dream material.
It really is. PGEC is the holy grail. The idea is a material that conducts heat like a glass very poorly, because glass is disordered and scatters phonons like crazy. But at the same time, it conducts electricity like a crystal very well, because electrons need an ordered path. Achieving both is the ultimate goal. People try all sorts of tricks. Complex structures with rattler atoms shaking inside cages to scatter phonons, or engineering lots of nanoscale interfaces.
Super low heat flow, super high electron flow. Makes sense. Finally, in this section, cooling down to very low temperatures, what are the hurdles using thermoelectrics way down there?
Yeah, cryogenic thermoelectric cooling, like below liquid helium temps. That's tough. The main problem is the figure of merit, ZAT, usually tanks at very low temperatures. Things like mobility, thermal conductivity, they all change drastically. But there's still some interest in specialized semiconductor elements. The book mentions that materials with high Debye temperatures might actually be better down there. which is kind of the opposite of what you often want at higher temps. Effective mass, scattering mechanisms, they all become super critical, getting practical cooling way down there. Still a really hard problem.
Okay, let's zero in on a specific material that's been a real star. Bismuth telluride by House. What makes it so important?
Bismuth telluride, yeah, it's the classic room temperature thermoelectric material. A real workhorse. It was one of the first semiconductors found with decent thermoelectric properties near room temp. And crucially, you can make both N-type electron-rich and P-type hole-rich versions with very similar, quite good figures of merit. Ideal for making thermocouples. Learning how to dope it precisely, like using iodine for N-type, was key. Back in the 50s, they got around 40 degrees C cooling below room temp just with Bi-R-D couples. A big deal then.
The outline says its band structure is trickier than the simple picture. How so?
Yeah, the simple models get you started, but Bi-R-D's electronic structure is actually pretty intricate. For one, the effective mass isn't constant. It changes with carrier energy and temperature. Early experiments showed results that didn't quite fit the simple theories. And there's strong evidence for a second conduction band, slightly higher in energy than the main one. These complexities affect how electrons and holes move and have to be considered for accurate modeling and optimization.
And diffusion in Bi-R-Ds, why does that matter?
Diffusion atoms moving around within the solid is important for a couple of reasons. When you make the material, you add dopants. Diffusion helps distribute them, but also when devices operate, especially at higher temperatures, like in generators, atoms, the bismuth, the tellurium, the dopants can slowly move around. This unwanted diffusion can change the properties over time, degrading performance. So understanding and controlling it is vital for long-term reliability.
Makes sense. Bi-T is also the basis for solid solutions. We talked about the general idea. Why are they so key for Bi-T?
Right. Solid solutions are great for lowering lattice thermal conductivity. And Bi-T readily forms them with similar compounds. Bi-T's mixed with antimony telluride. Bi-T's makes excellent P-type alloys. Bi-T's mixed with bismuth selenide, Bi-Euro makes effective N-type alloys. By carefully tuning the mix ratio, you can optimize performance over specific temperature ranges, often better than pure Bi-T. A huge fraction of commercial thermoelectric modules today use these Bi-T's-based alloys for both cooling and power generation.
So what have been the practical developments, getting optimal conductivity and ZT?
Well, over the years, there's been steady improvement through better material growth, processing, and understanding. Researchers figured out the sweet spot for electrical conductivity to maximize the figure of merit. The ZT values for the best Bi-Euro-based couples have climbed from maybe 0.6 in the early days, continually pushing higher towards and sometimes exceeding 1.0 through ongoing R&D.
And it's getting more interest now for power generation from low-grade heat.
Absolutely. There's just so much waste heat out there from industry, cars, electronics, often at relatively low temperatures. Bismuth telluride alloys work pretty well in that low to moderate range, say up to maybe 200 degrees C or so. So they're really well suited for converting that otherwise wasted heat directly into electricity. Huge potential for energy saving, environmental benefits. Maybe not for super hot sources, but for tapping into lower temp waste heat, or even things like geothermal or ocean thermal gradients. They're a key technology.
Great overview of the Bi-Euro story. Okay, let's shift to how we actually make these materials and measure their properties, which can be tricky. Starting with growth from the melt.
Right, growing from a molten state is pretty common. Simplest way, melt the elements, let it freeze. But for better control, especially getting impurities distributed evenly and aligning the crystal structure, which matters a lot for anisotropic materials like Bi-Euro, you use directional freezing. The Bridgman method is a classic. You put the melt in a sealed tube, often quartz, and slowly pull it through a furnace with a sharp temperature change. It starts freezing at one end, and the solid grows progressively along the tube. Gives you better crystals, better alignment.
And zone melting, how's that different?
Zone melting uses a small molten zone that travels along a solid bar of the material. As it moves, impurities tend to get swept along or left behind, depending on whether they prefer the liquid or solid. Pass the zone back and forth multiple times, and you can purify the material or get a very uniform distribution of dopants. It can also help align grains in materials like Bi-Euro. The loaded zone technique is where you add dopant to the zone itself to get a precise concentration throughout the final bar.
What's this constitutional supercooling issue during growth?
Yeah. That can happen when the solidifying material pushes impurities out into the liquid right at the interface. This impurity pile-up lowers the melting point of the liquid right there. If the overall temperature gradient isn't steep enough, the liquid ahead of the solid can actually get colder than its local melting point. It becomes supercooled. This can mess up the smooth growth, cause defects, non-uniform structures. Bad for performance. You need the right temperature gradient and growth speed to avoid it. The book even shows a diagram for bisum alloys.
Okay, avoid supercooling. What about sintering? That's powder-based.
Yeah, sintering is very common for things like SID sheet, PBT, even BiT alloys. You start with fine powders of your materials, press them into the shape you want. Then you heat this green compact to a high temperature, but below melting. Atoms diffuse across the particle surfaces, bonding them together, making the whole thing dense and strong. For materials like BiK alloys where crystal orientation matters, you need to control grain alignment during pressing and heating, often followed by annealing a heat treatment to homogenize things and relieve stress.
Okay, so we've made the material. How do we measure its properties accurately? Electrical conductivity first.
Right, fundamental measurement. To avoid errors from stray thermoelectric voltages, using alternating current, AC, is often better than DC. An AC bridge circuit lets you precisely measure resistance, and thus conductivity, by balancing impedances. The key is using a high enough frequency so any thermoelectric voltages don't really have time to build up during each AC cycle.
Makes sense. What about the Seebeck coefficient? How's that done?
For Seebeck, you need a known, stable temperature difference across your sample. Then you measure the voltage it produces. You might attach tiny thermocouples right to the sample to measure T at both ends, plus the voltage, or have the sample between a heater and cooler block, measure the block temps, and infer the sample gradient. The author notes that if the sample has low thermal conductivity, most of the temperature drop is in the sample, even with good block contact. But sample uniformity matters. How you make electrical contact matters. It requires careful temperature control and sensitive voltmeters. Sometimes they use chopped heat sources and measure the resulting AC voltage.
Tricky. And thermal conductivity. Isolating heat flow sounds hard.
It is. Several ways. Steady state methods. Apply known heat power, wait for temps to stabilize, measure the gradient, calculate lambda. Big issue at high temps is heat loss via radiation. Throws off the measurement, so transient methods are popular. The 3-omega-3 technique is great for thin films or poor conductors. You use a heater strip on the sample, drive it with AC current at frequency L. This creates temperature oscillations at 2A. You measure a tiny voltage oscillation at 3 off, which relates to the thermal conductivity. There are also radial flow methods. But yeah, always need careful corrections for heat losses.
What about thermal diffusivity? How is it related and measured?
Thermal diffusivity, kappa, measures how fast temperature changes propagate. It's thermal conductivity divided by density times specific heat capacity, same as peak, so sum T. It's often easier to measure than conductivity at high temps because radiation is less of a direct problem. Ångström's method is common. Create a temperature wave in the sample, measure how its amplitude and phase change as it travels. From that, you get diffusivity. Clever variations use Peltier elements to generate the wave, or even use the sample's own Seebeck effect to detect the temperature oscillations.
Cool. And the figure of merit, ZT itself, can we measure that directly?
Yes, there's a Harman method designed specifically for direct ZT measurement. You measure the sample's electrical resistance twice, once under near adiabatic conditions, no heat exchange, once under isothermal conditions, constant temperature. The ratio of these two resistances is directly related to ZDT. You might suspend the sample in vacuum, adiabatic, or clamp one end to a big heat sink, isothermal. Still need to be careful about heat losses through leads, etc., but it's a direct way to get ZT. It can also give you contact resistance info.
And finally, those thermomagnetic coefficients Nernst, Eddingshausen. What's the setup?
For those, you need your sample and a magnet, obviously, and you need to apply either a temperature gradient or an electric current. Then you need tiny, precisely placed voltage probes and thermocouples to pick up the transverse voltages or temperature gradients that appear, often done in a cryostat for temperature control. You usually measure adiabatic coefficients first, then calculate the isothermal ones. There's even a technique developed by Guthrie and Palmer to measure a thermomagnetic figure of merit directly by watching the voltage change transiently after switching on the current. Clever stuff.
Incredible detail on the experimental side. Okay, let's broaden out again materials beyond bismuth telluride, starting low temp.
Right, down in the cold, pure bismuth and its alloys with antimony are interesting. Their thermoelectric and especially thermomagnetic properties can be quite good at cryogenic temperatures. Bismuth's Seebeck coefficient, for instance, gets boosted by a magnetic field down there, so they find uses in specialized low-temp coolers and generators.
Moving up in temperature, intermediate range generators.
Yeah, mid-range, maybe a few hundred degrees C up to nearly 1,000 degrees C. Lead telluride, PBT, and its alloys, and silicon germanium, SiGe alloys, are the main players. Used a lot in waste heat recovery and famously in those RTGs, radioisotope generators for spacecraft. PBT is isotropic, same properties, all directions, high mobility. But ZT isn't amazing on its own. SiGe is studied a lot for high temp use, optimizing the siege ratio and doping.
And nanostructuring these helps. How does shrinking things down improve them?
Nanostructure-making features on the nanometer scale can be a huge help, especially for reducing lattice thermal conductivity. In things like PBT alloys, adding nanoparticles, making nanowires, or creating layered superlattices introduces tons of interfaces. These interfaces scatter phonons really well, blocking heat flow. If done right, you can do this without hurting electron flow too much. So you lower lambda, keep sigma high, boost ZT. Examples include adding C-STEAM nanoparticles to elast alloys or creating nanostructures within PBT itself.
We mentioned SiGe before. What's the thinking on their ultimate efficiency?
Well, researchers like Slack and Hussein did detailed calculations. What's the theoretical maximum efficiency for SiGe generators running hot, say up to 1300 K? They often focused on compositions like Tsai. Seemed like a good balance.
Sets a target, right.
Exactly. Gives a benchmark for what might be possible in high-temp waste heat applications.
Okay, then some more exotic materials. Skutterudites, clathrates, what's their story?
Skutterudites and clathrates are cool because of their complex crystal structures, kind of cage-like. Skutterudites often have naturally low lattice conductivity. You can stick guest atoms in the cages, rattlers that vibrate and scatter phonons without messing up electrical conduction too much. Adding pores can sometimes help too, maybe filtering electrons or scattering phonons more. Some filled skutterudites have shown really high ZT values. Clathrates are similar guest atoms trapped in cages rattling around, scattering heat very effectively. Some get close to amorphous thermal conductivity. Both N and P-type clathrates show promise.
What about half-Heusler alloys in the MGX family, also in the running?
Yep. Half-Heuslers are getting a lot of attention, especially for mid to high temp power generation. A challenge can be their relatively high lattice thermal conductivity. So people try nanolayering or substituting atoms like ZrHF and N to scatter phonons better. The MGRAS family, X equals psi, Cauchy, SESN, are also studied mainly for lower mid-temps. Making solid solutions within this family lets you tune the thermal properties.
And briefly, complex doped Heuslers, HMS, and organic thermoelectrics.
Complex doped Heuslers means adding multiple dopants to fine-tune everything, alpha, sigma, lambda, mapping out ZT versus temperature. Organic thermoelectrics are newer, pretty exciting. Big pluses: easy processing, flexibility, potentially low cost. Their electrical properties are still improving, but some organics are reaching power factors close to inorganics. Interesting for flexible or lightweight applications.
Wow, a really diverse material zoo out there. Okay, let's talk about putting these into actual devices, modules, and applications.
Right, you rarely use single elements. Practical devices use modules. Lots of small P-type and N-type legs, connected electrically in series to add up voltage, but thermally in parallel, so heat flows through all of them. Module performance efficiency for generators, copy for coolers, depends on the material ZT, yes, but also the operating temperatures, and annoying things like contact resistance and heat leaking between the legs.
Where do Peltier coolers really shine compared to standard fridges?
They have unique niches. Size independence makes them great for small things, like portable coolers. No moving parts, unaffected by orientation, good for boats, maybe aircraft. They can heat and cool just by reversing current. Useful. Very precise temperature control, good for scientific instruments, stabilizing lasers or sensors. You can stack stages for bigger temperature drops, and people are even looking at rapid pulse cooling with shaped currents.
And Seebeck generators, where are they used?
All sorts of places. RTGs for space, as we mentioned, using radioactive decay heat. Big area now is waste heat recovery, industrial exhaust, car engines, even solar ponds, turning lost heat into useful electricity. Material choice depends on temperature, obviously. Besides ZT, something called the compatibility factor matters for matching the generator to the electrical load. And thermopiles, arrays of thermocouples, are used as radiation detectors, characterized by responsivity, volts per watt, and detectivity, sensitivity. There are also those transverse devices where heat and current are perpendicular, sometimes used in fast detectors.
Let's look closer at those transverse devices. What's special about them?
Their neat trick is you can tweak their electrical and thermal resistance somewhat independently by changing their shape. Unlike regular thermoelements where they're tightly linked, this opens up ideas like making effectively infinite stage coolers or generators just by tailoring the geometry. Plus, you can make them really long by using a zigzag shape, which helps match voltage current needs.
How do you build these synthetic transverse ones?
Usually by combining two different materials with very different properties, especially Seebeck coefficient and conductivities. Often one material is much more conductive, electrically and thermally, than the other. You layer them in specific patterns, orientations. This creates a composite structure where the Seebeck coefficient is strongly anisotropic, different depending on direction. The overall properties depend on the layers, their thicknesses, angles. Performance is judged by a transverse felt of merit, Z-perp.
Examples mentioned using metals with semiconductors or multi-layers or embedded wires.
Right. Pairing a semi-metal or metal high conductivity with a semiconductor, different Seebeck, is common. You might make a multi-layer stack with thin alternating layers at an angle, or embed parallel wires of one material, like metal, in a matrix of the other, semiconductor. So in one direction, properties are dominated by the matrix. Perpendicularly, the wires dominate. This creates the needed anisotropy for transverse operation.
Okay, our final deep dive area. Nanostructured materials. We've touched on this, but specifically quantum wells.
Quantum wells, super thin layers where electrons are confined in one dimension. This changes their available energy states, their density of states. Theory predicted this could boost the power factor of us. But actually showing this experimentally has been tough. Fabricating perfect structures and measuring them accurately at that scale is hard.
We know nanostructuring reduces lattice thermal conductivity. What's the evidence?
Yeah, there's lots of experimental proof now. Making materials from nanoparticles, nanowires, or creating bulk materials with nano features inside, like grain boundaries, embedded particles, all demonstrably lower the lattice thermal conductivity. It's mainly because all those nanoscale interfaces act as roadblocks for phonons, scattering them effectively.
Quantum wires, especially bismuth nanowires, were mentioned with potentially high ZT.
Yes, theoretical calculations for very thin bismuth nanowires, a few nanometers diameter, predicted potentially huge ZT values, especially along the trigonal axis. Due to quantum confinement changing the electronic density of states, potentially giving much higher Seebeck coefficients than bulk bi while keeping conductivity reasonable. Theory also looked at bismuth alloy nanowires. But experimentally verifying these massive ZT values has been challenging. Results have been a bit inconsistent so far.
And superlattices. How do those layered structures affect heat flow?
Superlattices, periodic stacks of alternating thin layers, like bi-Euro ZPs. Again, the interfaces between layers are key. They scatter phonons, reducing thermal conductivity compared to bulk. How much depends on layer thickness, the period, and interface quality, roughness. Disorder within the layers might also play a role.
Finally here, notes on bulk nanostructures and the measurement challenges for nanowires.
Right, people are making bulk materials with nano features dispersed throughout, using techniques like mechanical alloying to create nanoparticles. This has shown some success in improving ZT in bulk, like in bi-Euro systems. But measuring ZT for individual nanowires, extremely difficult. Tiny size, making good contacts, measuring tiny temperature drops and voltages, it's a huge experimental hurdle. There have been successful measurements reported, like on electrodeposited bi-Euro nanowires, but sometimes the resulting ZDT values weren't spectacular. Shows there's still optimization needed, and better measurement techniques are crucial.
Okay, last topic, thermionic energy conversion. How is that different from thermoelectrics?
Thermionics is a different beast. Instead of charge moving in a solid, you use heat to boil electrons off a hot surface, cathode, into a vacuum. They travel across the vacuum and are collected by a cooler surface, anode, creating current. The appeal: no solid material for heat to conduct through, potentially higher efficiency. But you need emitters with really low work functions, the energy needed for electrons to escape. For cooling, you need even lower work functions. There's also solid-state thermionics, electrons crossing a barrier within a solid.
Early experiments, Mahan's work on refrigeration. Key findings.
Hatsopoulos and Kai got about 13% efficiency with a vacuum generator using biasodium carbonate electrodes back in the 50s. Showed potential. Mahan looked at thermionic diodes for cooling. Suggested if you get work functions around 0.7 eV, you might get decent cooling around 500 K. Pointed to things like electrides, alkalides with low work functions. Big issue in vacuum is space charge. The cloud of emitted electrons repels more electrons. You need tiny gaps, like illuminated at 700 K, to minimize this.
What about thermionics inside solids, trade-offs?
Solid-state thermionics avoids space charge, but brings back heat conduction through the solid. Advantage: can potentially use both electrons and holes. Cooling rate depends on carrier energy over the barrier versus heat conducted back. Mahan looked at multi-layer structures to manage heat loss. also considered solid-state generators.
And comparing thermionic and thermoelectric using equivalent parameters.
Yeah, you can define equivalent parameters for thermionic devices in II based on work function, barrier height, etc. This lets you define a thermionic figure of merit, ZIT, analogous to ZOT. You can compare a thermionic materials parameter I with the thermoelectric phi. Simple comparison might favor thermoelectrics if electron path length is long, but thermionics might win if their equivalent lattice thermal conductivity is much lower. It's complex.
Well, this has been an absolutely fascinating and incredibly detailed deep dive into the world of thermoelectricity.
Wow.
From the very beginnings, the fundamental physics, through the materials science challenges, the applications, and even looking at nanostructures and thermionics.
It really has. It's clear this field is constantly moving, always searching for higher efficiency, better materials, the journey from Seebeck and Peltier just noticing things to the complex materials and devices we have now. It's quite a story of science and engineering.
Absolutely. And on that note, here's a final thought for you, the listener, to chew on. With all the progress we're seeing in nanotechnology and materials science, what do you think will be the single most transformative application of thermoelectricity in, say, the next 10 years? Something to really think about. Thanks for joining us on The Deep Dive.